Hello, today we want to discuss the AM and GM inequality, or the arithmetic mean and geometric mean inequality. Let's start with a trivial observation. Observe that if we take x minus y, two real numbers, and take them, square them, then we get something that is bigger or equal to 0, because, of course, any number squared is bigger or equal to 0. So this inequality is equivalent to saying x squared minus 2xy plus y squared bigger or equal to 0. So let's take the minus 2xy to the right hand side. Then we have x squared plus y squared bigger or equal to 2xy. Let's actually write this in a different way. Let's write 2xy smaller or equal to x squared plus y squared. Now we divide by 2. Then we have xy smaller or equal to x squared plus y squared divided by 2. So basically, the geometric interpretation of this inequality says that the area that is defined by the rectangle with the sides x and y is smaller or equal to the average of the squares defined by the lengths of this rectangle. So maybe we draw this out. So let's take, for example, this rectangle here. That's the x, that's the y, and that's the area x and y. Now let's take this area of x squared. That's x squared. Then we have also the area of y squared, just that. Yeah, and if we average them out, they're bigger or equal to xy. Okay. So if we take instead of x and y, we take square root of x minus square root of y to the power of 2. That's, of course, also bigger or equal to 0, provided, of course, that we take x and y positives, so that we can square them. Then we have the following. The square root of x to the power of 2 is, of course, x. So if we just we'll just do it once. If we do it like this, then, yeah, we get just the x. I don't want to do this all the time, but for now, it's okay. Minus 2 times square root of xy plus y bigger or equal to 0. And then we get a similar inequality, just written as, let's take it to the right hand side. Then we have x plus y bigger or equal to 2 times the square root of xy. And then we reformulate the inequality and get square root of x and y smaller or equal to x plus y divided by 2. Okay, so this is just the case for n equals 2. And this is just playing around a little bit of exploring how to use the positivity of the square of any real number. But now the question becomes, how can we generalize such an inequality? And one possible generalization is, because this here is, of course, xy to the power of 1 over 2. Let's write it out. Possible generalization is that we take n such numbers, and then we take them to the power of 1 over n, and that would be smaller or equal to the summation of these numbers divided by n. Okay, let's try to prove this conjecture. And okay, so our strategy will be to first prove this only for certain kinds of n's. So let's take a look at, for example, a1, a2, a3, and a4 to the power of 1 over 4, and try to use the AMGM inequality that we established for the case n equals 2 and apply it twice. So this is the same thing as a1 a2 a3 times a4 to the power of 1 over 2, and then to the power of 1 over 2 one more time. Okay, so now what we want to do is to write this out in the following way. We have a1 a2 power of 1 over 2 times a1 a2 to the power of 1 over 2, and all of this is to the power of 1 over 2. Now we have what we want to do now is we want to apply the outer AMGM inequality. So we take this as x and we take this as y, and you want to remember that x and y to the power of 1 over 2, which is our outer square root, that's smaller or equal to x plus y divided by 2. Now let's apply this in our case. This gives us just a1 a2 to the power of 2 plus that's actually a2 a3 and a4 to the power of 1 over 2 divided by 2. Okay, now we apply the AMGM inequality to each of these terms inside of the our brackets. So this will be our new x, this will be our new y, and let's do it one more time. So this is smaller or equal to a1 plus a2 divided by 2 plus, now we do the same thing here. We say this is x, this will be our y, so this is just a3 plus a4 divided by 2. In all of this, we still have our outer division by 2, and this becomes ultimately a1 plus a2 plus a3 plus a4 divided by 4. Well, you can calculate this out. We just we bring them basically to the, we can have like the summation, and all of them are just divided by 2, and then divided by 2 one more time, and this just gives us the 4. I think this is quite let me know if it's not obvious, but I think it is obvious. So let's call this inequality 1. We used it here, and then we used it here twice. Okay, we can try the same thing one more time with, for example, a1 a2 until a8 to the power of 1 over 8. We apply the AMGM inequality here as well. How do we do that? We base a1 till a4 to the power of 1 over 4 times, actually we could do these steps in one go, but let's just add this additional step also in between. That's just a5 till a8. That's to the power of 4, and then overall to the power of 1 over half, or 1 over half, or 1 half times 1 over 4 is 1/8, so that's okay. Now we write this term as a1 till a4, this to the power of 4, times a5 till a8 to the power of 4. And then, of course, we have our outer square root to 1 over 2. Now, what do we want to do is that we just consider this here to be x and this here to be y. And Then we apply the AMGM inequality on that, and we say, okay, that's just A1 times A2 times A3 times A4 to the power of 1 over 4, because, well, that's just the entire number, x plus the y, which is A5, A6, A7, A8 to the power of 1 over 4. And all of this divided by 2. Now, what we want to do is to apply our previous result with for the term n equals 4, because we have shown that the inequality holds for n equals 4. So we know that this here, let's actually use the green color here. This here is smaller or equal to a1 plus a2 plus a3 plus a4 divided by 4. And this here is smaller or equal to a5 plus a6 plus a7 plus a8 divided by 4. Okay, so we have 1 over 2 times 1 over 4 bracket a1 plus a2 plus a3 plus a4 plus a5 plus a6. Well, I didn't have to write this out actually, but whatever. Okay, so this is just 1/8 times the summation of this. Let's just write it out as a summation from 1 to 8 of these AIs. Okay, so what we have established, this is true for n equals 2, 4, and 8. And actually, by induction, we also have shown that this is true for all n's of the form 2 to the power of k. So this is generally true. We can always repeat this and use this induction argument to generalize this on all of these numbers that have this form. And k, of course, bigger or equal to 1. Okay, so what we want to do now is to show this also for the gaps between these two to the power of k. So let's take general general real numbers. Actually, yeah. Okay, now we need to show this inequality for all n. Now let's take n smaller to the power to 2 to the power of k. And okay, for some k, what we need to show is that let's write it in a different way, that the inequality holds for these for these. No, actually, let's write it out. Smaller or equal to the summation of these a's divided by n. Okay. For that, we define a new sequence. Define alpha i's such that I goes from 1 to this 2 to the power of k. By alpha I equals ai for all I in 1 to n. And for all the other i's, we have to define the average of these ai's. This is a1 summed up to n, an divided by n, for all I in n plus 1 till 2 to the power of k. So why do we need to do this? Because now, since we have now these alpha i's go from 1 to 2 to the power of k, and we know that the AMGM inequality holds for all for numbers in the case n equals 2 to the power of k. So we know that alpha I, let's write it out actually, to alpha 2 to the power of k over 2 to the power of k. This is smaller or equal to the summation of these alphas. Okay. So since let's write this out. Since all of these, let's write these alpha i's actually out. So we have a1 till an. Then we have all of these averages. So alpha I plus n plus 1 up until alpha 2 to the power of k. All of this is 1 divided by 2 to the power of k. That's smaller or equal to a1 summed up to an, and then alpha I plus n plus 1 plus alpha 2 to the power of k divided by 2 to the power of k. Okay, so all of these, let's write them out. They are just all constant, which is the average of these ai's. So there's just a2. All of these are a. So this is an a, and this here is also an a. And how many times do we actually multiply them? Precisely 2 to the power of k minus n. This is the amount of times that this a is multiplied here. Okay, and on the other side, this here is just 2 to the power of k minus n times a. Because when we sum them up, we don't potentiate them. We have just the multiplying them by that factor. Okay, so let's write this out. This is just a1 times n. That's just 1 over 2k, and times a to the power of 2k minus n divided by 2 to the power of k. That's smaller or equal to a1 summed up to an plus 2k times a minus n times a divided by 2 to the power of k. This here is, maybe we'll write this out as in a side calculation. So we have n a equals a1 up until an divided by n. That's just equivalent to saying that na equals a1 summed up until an. Well, and so this actually cancels with all of these here. And then we get that a1 times until an to the power of 1 over 2 to the power of 2k times a minus n to the power of 2 to the power of k smaller or equal to 2k times a divided by 2k, and that's just a. Okay, so now what we want to do is to bring the a's to the right hand side. Then we have a1 times an to the power of 1 over 2k smaller or equal to a times a of n divided by 2k minus 1. And so this is just a to the power of n divided by 2 to the power of k. Okay, so now what we have now is just a1. If we take all of this and take the power of 2 to the power of k, get the multiplication of all of these a's, smaller or equal to a times n. Now let's take the square root. And the square root is just a1 times an smaller or equal to the power of 1 over n, smaller or equal a, and a is of course what? It's just the average, and that's a summed up until an divided by n. And that's the an-GM inequality in n terms. Okay, just a quick follow-up on the induction argument for n equals 2 to the power of k. We said that we proved it's true for 2, for 4, for 8, and then we said by induction argument it's true for all n's of the form 2 to the power of k, where k is a positive number. We want to give a few details for this argument. So if we have a1 times a2 until 2 to the power of k over to the power of 1 over 2 to the power of k, what we want to do here, and we did this also for our transitions from 2 to 4 and from 4 to 8, is that we want to split this 1 over 2 to the power of k, namely by splitting this into 1 over 2 to the power of k minus 1 times 1/2. And here in the product, we want to make the split in the middle. So we go from a1 to a2 to the power of k minus 1. And then the next term is 2 to the power of k minus 1 plus 1 till 2 to the power of k. And so all of this to the power of 1 over 2 k minus 1, and then 1 and all of it to the power of 1/2. So, okay. What we want to do is we want to write the internal product a little bit differently. We want to make the split here, and then we distribute the power of this product. So we have a1 to a2 to the power of k minus 1 to the power of 1 over 2 to the power of k minus 1. And the same thing also for the other term that we split it. And all of it, of course, it stays to the power of 1 over 2. And so we want to apply the AMGM inequality for these two terms. So we have 1/2 times this thing here plus this thing here in brackets. Okay, now we want to use the induction hypothesis. Since we have now 1 over 2 to the power of k minus 1, we can use that. And then it was also the case for where we proved the inequality for n equals 8. We used the fact that it holds for 4. And when we proved 4, we used the fact that it was true for 2. Okay, so now we apply the AMGM inequality to this term here, and then we get 1 over 2 to the power of k minus 1 times the summation of all of these terms, and we do the same thing for this term. This is 1 over 2 to the power of k minus 1 times the summation of these terms. Okay. Then what happens next is we pull this 1 over 2 to the power of k minus 1. We have it twice. We just pull it out. Multiplying it with 1 over 2, it becomes 1 over 2 to the power of k times the summation, thus giving us the inequality that we wanted, and thus completes our induction argument.